Hi everyone. We are very happy to have invited Wenlong here to present his great works. Wenlong is a PhD candidate in computer science at Stanford University, advised by Professor Feifei Li. He received his BA in computer science from UC Berkeley, where he has advised by Professor Deepak Pathak, Dr. Igor Mordach, and Professor Peter Abil. He studies the intersection between robot manipulation, foundation models, and 3D computer vision. His works have won the Outstanding Paper Award in Robot Learning at eQua 2023, the Best Paper Award at the Coral 2024 LEAP Workshop, and the Best Paper Finalist at eQua 2025. He received Stanford School of Engineering Fellowship and was selected as a finalist for the NVIDIA Graduate Fellowship and the Citadel GQS Fellowship. Now, I will pass the floor to Wenlo.
All right. All right. Thank you, Roger, for the introduction and thank you for having me. So today I'll be talking about our recent work on 3D world modeling for robotics. And just to get started, oh, by the way, this is like one of the first iterations of the talk, so um, please feel free to interrupt me if there's any question. And please also bear with me if there's anything that's unclear. And yeah, feel free to just interrupt me at any time. Yeah, so just to give some motivation, I think as a field, it's really been one of the North Stars to build robots that operate in the open world. And I think this video from Stanford Robotics, a personal robotics program, almost 20 years ago, really exemplifies the pursuit, where the robot enters a household environment and just tidies up the space. All was great, except here it was tightly operated by a grad student. And I think this pursuit can really be traced back to almost the beginning of the AI era. So, I mean, the beginning of when AI was kind of invented in the first place, where this is like Shaky the robot from I think from the 60s, also trying to do kind of it started the pursuit. And from the recent year, I think, in fact, we have made tremendous progress, especially with end-to-end policy learnings. Uh, like, for example, diffusion policies with its wide adoption can really effectively model the multimodal action distribution and expressive enough to absorb very complex actions that being demonstrated in a data set, as well as the emergence of vision language action models, VLA models. These are like fine-tuned from usually from VLMs to leverage its rich semantic knowledge. And I think it's got to the stage where it's super impressive that basically any task we can demonstrate, then the policy can learn it. So I think this release from physical intelligence and TRI on their like Pi 0.5 and also the LBMs show some of the really impressive tasks I found. And but at the same time, there was also the kind of uh, the data challenge where like we can absorb any data we give it, but how much data can we really give to these models? So I think this slide, I think this animation from Ken Goldberg really shows how big the data gap is if we want to train kind of frontier at a really foundation model scale, kind of like the LLMs. And this is comparing the data set from in robotics to the data sets in VLMs. But this is just I think this is a great comparison. But I think there is also some few nuances to really consider here, right? Like VLAs are not built from scratch. They're built from already from VLMs. So technically, we don't need to. It's possible, totally reasonable to assume that maybe it doesn't really need that much data because we already have all of this like really important knowledge prior about how the world works, etc. But at the same time, we are also making an implicit assumption that when we compare the data like this, that the transfer efficiency between robotics and language models are the same. And usually people like I don't think people really believe this because they're definitely two different domains. But it's really hard to really quantify um, how do we think about the transfer efficiency? Because I think the typical paradigm that we want to consider is we pre-train on some large data sets and then at test time uh, with more data we can with just very few data we can kind of fine-tune the model to perform efficiently at downstream tasks and eventually maybe even zero shot. But to really quantify this, I think when I was digging through the literature, I think there's one paper actually from 2021 from OpenAI. Uh, I think there's a great paper that they measured how like they really took an initiative to really measure how the transfer efficiency works in language modeling. So this is like called scaling loss for transfer. And I think they have some great setup. Basically, how they measure is that they pre-train a LLMs on I think on just web text, and then they fine-tune it for Python program generation. I mean, this is from 2021, so there was no like it was like still the GPT-2 era. And then, and this is of course like a small language model because they wanted to really um, like really in-depth comparisons. So they ran a lot of experiments, but they're also like claiming that this could possibly generalize to larger model settings. But this is some few assumption to keep in mind. I think that what they showed is that basically if you pre-train more if you pre-train on some large data set, then the more data there is in the pre-training, then the more effectively it can be fine-tuned to the test data set. And this can be really quantified by how much data. I think they have a great metric. Basically, there's like the pre-training scale, which is denoted by S, and also the task-specific fine-tuning data denoted by D. And then you can really compute after you run experiments, you can really compute from the empirical kind of the observation, what will be the equivalent from scratch data it will require to get to the same performance. And then when you divide that by the actual data set being used in the fine tuning, you can get a that's a uh, unilist metric that can measure kind of how efficiency it can be fine tuned. And then I think it's hard to really study this in robotics unless we have a really kind of like systematic investigation. And I feel very fortunate and very grateful that like TRI from this past year published this I think great technical report on careful examination of their large behavior models for this uh, for exactly this setup. And this is one of the figures from the paper where they vary kind of the number of amount of pre-training data. And what they observe is very similar to what people observe in language model setup. Basically, the more data there is in the pre-training, uh, and at test time, you can more effectively to fine tune it to the test setting. And with the same amount of data, you can either get to a better performance, or with the same target performance, you can use less data in the fine tuning. But if we take this plot, right, and then compute the transfer efficiency as I was showing, like from their 2021 OpenAI paper, then we can see how much it differs. I think the good news is that both domains transfer better with more data in the pre-training. But robotics actually has 100x worse transfer efficiency at its current like pre-training objective and also the pre-training data sets that TRI was using. And with more data, we can actually match NLP setting by scaling to 74,000x data of what TRI already had when they did the work. and that's equivalent to 125 million hours. I mean, it sounds bad, but to be honest, like with so much capital being put into the community, into the industry, it's actually now like the worst thing to think about. But still, like this is on the assumption that every bit of data you add brings the consistent diversity to the pre-training at the level of what the current pre-training data set already has, which is really from the aggregation of the whole community. And another assumption is that this fine-tuning setting that TI was studying, so all of these data points that we got is from a tabletop simulation tasks. Uh, like, and I mean, it's not really the whole suite of tasks that robotics really needs to do. And how does it transfer there? We don't know, but I really will be hoping to get more metric. But this is one of the first way, I think, to really quantify the differences between the setup that we have compared to, for example, domains like NLP. So as people in academia, right? I mean, 125 million hours may be justifiable, but like I mean, in industry, but as people in academia, we really need to, I think it's a really good way to think about how can we do better, right? Like for example, what will get us to be higher on the ramp? And one hypothesis here is world modeling. So let me start with some few comparisons to why that's more similar to next token prediction compared to, let's say, LLM pre-training. So first, let's define really what world modeling really is, because I think this term is just like being super overloaded right now. So world modeling, in my opinion, is pretty clear that it takes in the current state and current action, and it should output the next state. And in contrast, the policy would take in the current state and current and output the current action. So here I'm kind of not really using observation versus state because I think we just want to simplify the setup. But if you care about that, then it should really be the observation. And I think compared to the setup, like one really important kind of feature that a pre-training objective should have is that I think it should be really independent of the objective that's being done at the test time when we're doing the pre-training. For example, in LLMs, this objective is next token prediction. And when we do next token prediction, we don't really care what's the downstream task. For example, whether that's question answering, machine translation, summarization. So all of these are tasks that classically people care about in NLP, and they're all being kind of like subsumed by this next token prediction objective. And I think similarly in world modeling, if we do world modeling, then this can be easily applied to setup where like maybe children play with toys, and sometimes like we just do some fidgeting with the pens or throwing water bottles. All of this teach us how the world works without really caring the downstream objective yet. And of course, like LLMs can learn from diverse non-expert data. So whether that's good data or bad data, they should all be there in the pre-training. Like for example, the good data from maybe from the books and from like code coding domains, or just like random chat, right? If that's even allowed in the pre-training, but I think possibly they're all being included right now. And similar to LLMs, world modeling in robotics could include really high quality data like demonstrations, or it can also include data from different embodiments like robot dogs, humanoid, or just like data from egocentric human data. And I think in contrast, policy pre-training can only from learning from expert-only data because that presents on high quality behaviors, and that's typically for that typically requires like humans having some tasks in mind as well. And another thing that I think that's being slightly overlooked is a unified modality. So if we think about text or language models in general, uh, whatever task it is, I think it's just fortunate that in NLP that people have this so everything can be kind of so both the state and actions can be represented in text. So there's no we don't really need to care about state or action. So when people do RL in LLMs, for example, although it could be formalized with like either like something is state, something is action, but it doesn't really matter because everything is just text. So we can easily do it. But in robotics, we're facing this really scattered challenge of there's really different action spaces. I think for observation space, maybe we can be okay with just having vision as input. I know other modalities could be really helpful, but let's say I think people generally agree that we at least need to have vision. So let's say that observation space is pretty clear, but what about action space, right? Like it can be really any degree of freedom for any robot that we build, and even for the same number of dots, we can have different geometry of fingers. It could be longer, it could be shorter. It's the same dots, but it really changes the behavior quite a lot. And that's like a little concerning if we want to have a really unified pre-training. So the natural question is that can we also similarly have a unified modality? Yeah, this is alluded to something that I'll be talking about mostly today, but let me give another, I think, motivation that I think that's really important as well, but also being less studied, which is a world model also enables extracting test time inferences to synthesize solutions or behaviors that's like beyond the data. So why is this important, right? Because I think from the beta lesson that this is like people usually like to use beta lesson. I mean, it's a trend right now, but I think we can go with it. Like I think like people usually interpret that, oh, we just want learning, right? But in reality, if you look at the beta lesson, what Rich Sutton was really saying is that we need both learning and search. And why is that the case? Because if you think about, for example, in LLMs, then learning is definitely super important. We need to scale learning, right? That's equivalent to scaling pre-training. But at the same time, if you think about the agents that we use today, only next token prediction is not enough. It needs to do, we need to scale also test time compute. It needs to reason about the situation for now. Uh, so even in LLMs, that we cannot just compress everything into the pre-training or into the offline training, whatever we do, and then expect it to just work test time. We need to, even in LLMs, we need to have this test time inferences that we need to do to synthesize solution, particularly for the situation we face. But if we believe robotics is really harder than NLP, then it's possibly assumed that we cannot cover just all the cases from training time. And I also really love this diagram from Sergey Steve R. course at Berkeley. So basically here he was showing exactly this this spatial lesson slide, but also he was making this contrast between learning and search. Basically, learning is using data to extract patterns, and search is using computation to extract inferences. And data learning allows us to understand the world, and search really leverages that understanding for emergence. And why is this important for robotics, right? Because if you look at this really fantastic demos from physical intelligence, we can really have robots do these really complex tasks with really novel solutions. For example, like wrapping the sock on the gripper to invert it because the robot they choose to use only have jaw grippers. And it's not like dexterous hand, multi-finger hand, so it cannot just flip the sock, invert the socks like we do. Um, and then also it could like mashing the plastic bag on the table to open it because again it doesn't have the multi-finger hand. But these are really novel solutions, right? But they're demonstrated by the data by the demonstrators. So this is really human ingenuity. And if you want to then the natural question is how do we autonomously produce such emergent behaviors at test time? And I think the key here is that we need a model that supports the counterfactual what if queries, so that we can do this kind of reasoning at test time to reason about how the actions changes the environment and synthesize solutions from there. and that is a world model. Okay, so with that, all of this, I know it's super long, but with all the motivation, we can get into the work today that mo I'm mostly spending time presenting. This is PointWorld scaling 3D world models for in-the-wild robotic manipulation. This is really a work has spent actually 18 months in my research and in my PhD, and it's actually the only project I led pretty much in that 18 months. So technically in the first 12 months, but that's the only project. So we really think that this is important, and we really want to take time to get to a good state. To Yeah, and so yeah, let me just dive into it. So the input is pretty simple. I mean, the goal we want to achieve is actually pretty simple as well. The input is a RGB capture. It could be one image, it could be two image, or multiple images. It doesn't really matter. And the also another input is that there is a description of the robot, of some robot we care about. This is a test time. Like it's not for a particular robot. Like at test time, you can swap it with maybe a new finger or something like that. Um, and then, so this is like, of course, with a robot URDF. And also we assume as input is a set of robot actions because this is world modeling. And then the output we want from these inputs is a full scene simulation of what will happen in the scene by responding to that robot actions for that particular robot embodiment and for that particular scene. So, so what is really an action, right? Like when we talk about action here. So in world modeling, people use text as actions and navigation as actions. And these are all great. I mean, they're used for different purpose, but to support this counterfactual reasoning, they're possibly too coarse for manipulation purpose. And people in manipulation, people also often use anti-factor pose as actions and join commands as actions. So for anti-factor pose, so naturally it doesn't capture the gripper geometry, whether that's longer finger or shorter finger, different geometry of finger. It's all captured. I mean, it's not really captured in this few numbers, and it doesn't cover the case where what if there are multiple grippers, right? Then you have like multiple poses, and that's like um, yeah, that's like a different action space. And similarly for joint space actions, that's also pretty commonly used. It also doesn't capture gripper geometry, and it also poses the question about what if that's robot has different kinematics, different number of degree of freedoms. So, so why is this important to think about actions, right? Like, I think another kind of thing I would want to think about is how do we, what are we really thinking about when we collect the demonstrations? Like, we can easily collect demonstrations for very different embodiments. So why is that the case? Like, we don't really need to care about like number of degree of freedoms. We only care about the task at hand and the robot we can control. I think one kind of argument here is that we're really thinking about the interaction geometry in 3D. So we're thinking about the actions actually in 3D rather than a particular like joint space actions. So this is what we try to instantiate in this project. Basically, we want to use a 3D representation for actions, and we ended up using 3D flows. So why is this nice? Because it's embodiment-agnostic action space, so you can deal with easily different embodiment, different geometries, different kinematic structures, hand geometry, a number of hands with the same action space, and you can have different number of points because the architecture is kind of invariant to that. And so how do we get the flows, get the action flows? So actually, there's no learning here yet. Because we have the robot URDF, we have the mesh, and we just sample endpoints on each link, and then we compute the forward kinematics, and then we transform the points for each link to form the point flows. So this is the action representation. And to really kind of like work towards the goal of unified kind of modality for this pre-training or for this world modeling, uh, we also want to use similar things for state. So uh, state is here a point cloud, a static point cloud from the scene, uh, built from the RGBD capture, and this is something that yeah, and then the input is the static point cloud and the robot. But as I was talking about for the robot, we also analytically compute their point flows given the known robot URDF, and what's being predicted is the scene into the future. So the architecture is also basically exactly this. Uh, Somehow it's not playing, but this is supposed to be video. Okay, yeah. So the input is robot flows part plus a point cloud that's being built, and we literally just concatenate them together into one single point cloud, and this is processed by this transformer called for point cloud called PTV3, and what it outputs is a full scene 3D scene flows, point flows for the scene. And I think there are a few properties that's this is a very simple formulation, but there's a few properties that I think it captures that we care about in manipulation, which is first of all, to really do this, right? It needs to first understand what is the object I'm manipulating, because there's no segmentation mask being given, so it needs to do object segmentation, detection segmentation, all implicitly in 3D, and it needs to estimate the material property with the data it's being pre-trained on. For example, this is like deformable object, so how should it deform? And if it's a articulated object like a fridge here, it needs to estimate the articulation structure from that from the same formulation. So there's no explicit articulation estimation here, but to do the task, you really need to do this implicitly. And also, I think what's interesting is that when you're dealing with like a large object, inevitably that there it has to be like a partially observable. For example, if it's a large box, then you probably wouldn't see the back panels of the box. So it needs to do implicitly also shape completion to support the contact reasoning of how the hand interact with that object. And also, if in over here, the robot is kind of holding a ball also with an object in it. So it needs to not only reason about object dynamics, it needs to also reason about this in the context of how the robot is moving and how the whole thing interacts with maybe gravity as well. And lastly, also gravity here. I think there's also a clause, so there's also some deformable property capture here. So we have some um, many rollouts that we have on the website, so feel free to check them out. Here I'm going to show some of them. So all of these rollouts are from a single checkpoint of the model, and all of them are unseen rollouts in the training data. So here, the input is a two RGBD images from the side views. This is one sample from Droid. And then here, when the robot is moving like this, it needs to estimate how the cloth is getting manipulated. And this is the example I was showing, but with a larger view, with a ball and also an object in the ball. And here for this large box, if we rotate it to the back, we can see that the hands are visible because we're sampling that from the known robot URDF. But the observations are, the scenes are partially observable. I think this one is also interesting uh, because this is unseen rollouts. This is like this is also unseen rollouts, but the robot here is kind of holding this basket and shaking the basket while there are many objects in the basket. So it's really hard to predict this. It needs to reason about how the object come into contact with each other, how they come into contact with the basket, how does the gravity affect all of this as well. So why is this exciting time to study 3D world modeling now? Because I think previously people wanted to do this as well, but there wasn't enough data. So I think it's particularly exciting time now because right now we have the tool. We're graduating towards like we're having the tools that are being mature enough to provide the data for us. So here I'm showing some of the works that we're using in the project from 3D vision that really made this possible. So this is a foundation stereo, VGT, code tracker 3, and point transformer V3. These are all from the recent years, wonderful works from the recent years. And we're using all of them to annotate the Joy data set. And we can annotate up to 60%, slightly more than 60% of the whole Joy data set, including both success and failure data with almost simulation level depth and camera poses. So here are some comparisons to the original droid depth and also the calibration. So the calibration here actually is from they have a V2 from the yeah from the authors, and we're using that latest version, and you can really see how much how much the new vision models are getting us better depth and also camera qualities, camera poses. And of course, we're also adding large-scale diverse simulation data from behavior. This is some of the largest data sets in simulation with really photorealistic and diverse household environments. So in total, we are also doing some filtering on top. So in total, this amounts to 500 hours of accurate 3D interactions. And mostly what we filter out is the static, kind of the static scene, because there are often sometimes that we are doing just like some motions in the air that's not really doing some contributing to some meaningful interactions. So after we filter all of those out, we have roughly 500 hours of accurate 3D interactions. This is still so I would say just very small scale compared to what 2D models are trained in. So but I think it's already one of the largest in 3D. And I'm hoping to have more with the advances of these 3D models. So with all of this, we can now investigate how do we properly scale them up and what's the property when we scale up these 3D models, 3D world models. And I think the nice thing here, thanks to this large data set, is that we can really have rigorous investigation. So by rigorous, I mean that because this is like dense prediction and there's a large test set, actually 10% of that whole data set, we can have really standard errors that are on the order of 10 to the negative 5 meters. So this is several times thinner than human here. So if we ever compare two setup or two different models, it's really clear that one is better than the other because the standard errors are so small. So we charted a roadmap to scale this 3D world model, and the most important lessons we found. So we started with the graph-based neural dynamics model that's been popular in this domain when training dynamics models. And then we modernize it with more modern point cloud architectures, and we can see if we use PointNet, it can slightly decrease it decreases the error because this is like more larger scale scene. But then if we move to the latest PTV3, it can really make the error so much smaller again. And then we also need to tune the training objective because for the scene we have, as you can probably imagine, that it's a large scene, and the robots are typically only interacting with a very small region of the scene. And then we need to really emphasize on the training signal on the points that are moving. So and then there's also some additional noise from the 3D annotation because this is all training from the real world data. And then So we need to add a certainty scaled loss, and also we need to emphasize the moving part. And also all of them are combined with Hoover loss to further help with um, the potentially noisy like labels. And what we also found useful is adding image features. So this image features, because we're training the 3D world model, the point cloud models from scratch. So this is unlike, for example, in video model cases, people can start with some pre-trained video model. So we found all of this. We found that we need some sort of priors about the semantics of the scene, and Dino V2 and V3 really help here. So we tried Dino V2 with different model sizes, and Dino V3. Uh, and then what we found is that if we add in multiple layers from Dino V3, VITL, then that contributes the most. And of course, it's also very important to scale up the model size to really ingest all this data that we have. So when we dive more deeper into the backbones, we can see how switching to this PTV3 or more modern transformer-based architecture is important, because with almost a similar memory footprint and like 1.8 amount of flops, we can scale the model size to almost 300x of the original GBND baseline. And that's really important because we want to ingest all this data, and that can really bring down the error. And also, it's important to represent the action spatially. So here we're comparing this action representation between, so we have a few baselines. So what kind of wins out in the end is gripper representing the actions as point flows on the grippers. We also compare that to representing them on the full body of the robot with 500 points and also 3,000 points, as well as the low dimensional baselines with joining positions and anti-factor pulse. So what we found is that, so this is like training a single model on both embodiments. So this is one is like the Franca being used in Droid, and the other one is the Galaxia, like I think R1 Pro being used in behavior. So there's like very different embodiments. And if we train them with joint positions, we can see the errors are relatively large, really. And then if we train on anti-fragile pulse, that's slightly better and intuitively also more aligned. Although one is one hand and the other one is like two hands. And then if we train it on full body kind of point flows, it's a lot better in simulation because the scene is really clean, so there's no noise at all. So that actually contributes a better transfer. But for the real world, actually, that doesn't. It actually makes the things worse because it's very noisy kind of scene, and then I mean even after the annotation. So and then it's also, I mean, the contact is only happening at a very small, not only a very small region of the scene, but also a very small region of the robot. So we found that this is making it harder for the robot for the model to concentrate on where the interactions are happening. So in this more noisy setup, so that actually make things worse. But if we switch to representing actions as flows only on the grippers, that actually to be the best case. And this really enables positive transfer across different embodiments. And with this evaluation, we can also try a lot of different setup to really probe the generalization properties. So again, we're training on this both domains, droid and behavior. So droid denoted by D, behavior denoted by B. So we can investigate both so all these different settings was the in-domain generalization, was the cross-domain generalization, and what if we held out one lab's data from Droid? So, so after looking through Droid's data set, we decided to held out Joseph's lab from I think his lab is in Korea, so that's like the furthest from the rest of the Droid teams. So we decided to make that as held out because it kind of maybe minimize the contamination issue. So if we held out that data set, a small subset of Droid, what would happen if we pre-train on different kind of setup, and what's the generalization property there compared to if we just we just train specific model for his lab's data. And we can investigate this in both like zero shot and fine-tuned setting for this. There's a lot of numbers here, and there's a lot of interesting conclusions. But the TLDR for the most important one or the most interesting one I found is that by having this like large data set, I think here, if we train on the droid, if we care about some downstream kind of unseen data in the real world, then if we train on only the droid or droid plus behavior, it can almost match if you were to like train a particular model from that lab. And this is all zero shot. So you can use this model zero shot basically if you use the similar droid setup to match a model particularly trained for that setup. Of course, in the distribution of the task that droids is collecting. And then um, if you fine tune adding only 5% of the fine tuning data, you can outperform the from scratch baseline. And also another point that's interesting is that simulation pre-training. So if we do some simulation, adding simulation pre-training, that enables 20x less compute to compared to the from scratch baseline on the real world scene. But real world data is still indispensable because I think if we only do simulation pre-training, it doesn't really work. And then what's also interesting is that the trend also continues with more data and larger model. So we kind of do like separate this two cases. So on the left side, we're keeping model size to be the same, and we vary the amount of different fractions of data that we provide to the model training, and we evaluate on the same task set. You can see that with more data, it's having this close to linear like performance increase with in this log space. And similarly, if we keep the models, the data size the same, we can also investigate how what will happen if we scale the model furthermore. For example, if we scale it down, we start from 50 million parameters. If we keep scaling up like this, it also decreases almost linearly. And this provides some signal that it can further improve with more data and larger models. And also, like we are doing this chunk prediction in one forward pass for 10 steps into like in the one into the future for 1 second. So the DT in this model is 0.1 second. So we want to see why if this formulation is important to the setup. And this is very similar to what people have observed when training policies, because using this chunk prediction does help in both training and inferences because it reduces the rollout drift. And of course, what's also important here is that it improves computation efficiency a lot because alternatively, you have to do autoregressive prediction to chain them across different time steps. And now you can still chain them, but you only need one forward pass for each 1 second. And because this is like a 3D model, so it's also interesting to take to investigate how it deals with partial observability. So to study this, we trained four models. One model trained with only one camera over here, and one model trained with a fixed, always two cameras per scene, and another model trained with three cameras, and like another model trained with randomized number of cameras. And so we want to kind of plot this like 2D matrix. And so the other axis that we want to see is in evaluation setting, what if we fix one camera and we fix to two camera or fix to three cameras? So we evaluate all this model in all of this setup. So the takeaway here is that the model will perform the best if we randomize the number of cameras in training. Uh, that's kind of intuitive because it deals with different amount of partial observability when implicitly segmenting the object or estimating its material property. More views does give you more information, and explicitly that shows some alignment in the space as well. Uh, and then what's also interesting is that it's robust to different levels of partial observability, also at test time. So if you look at the case where we train on, let's say, I think one camera you can see that's it's not as clear, but it is still decreasing in evaluation time. But for two cameras, the trend is really clear. So if we train on only two cameras and we evaluate with one camera, the errors are relatively high. But if we get to evaluate also with two cameras, it decreases quite a bit. And we can add more cameras at test time. For example, if we add three cameras, it can further decrease the errors. So that shows at some level it has some level of robustness to different amount of partial observability. So how can we use this for action inferences, right? Like I think one model is usually there's so many ways you can use it. You can use it as pre-training. You can train RL within it. You can somehow adapt it to like a policy. There's so many different designs here. But I think this work we want to focus on the world modeling itself. So we just want to go with the most basic baseline that doesn't involve so many moving pieces of how do we design the policies, etc. I think those are still super important, but it's just hard to kind of compare them to mix them all together. And because we can only evaluate them with success rate. So that's like also a very like bad signal if we don't have the effort or resources to do the systematic evaluations. So we'll go with the most basic option of just integrate PointWorld with model-based planning. So this also is without demonstrations or fine-tuning. So these are not this is I know this is not some of the most impressive tasks, but all of these behaviors are being generated fully at test time. So without particularly training them, training this behavior. So this is like for non-prehensile pushing, deformable manipulation. Oh, this is for articulated objects. I think the typo here. And also some two use cases where it needs to think about object dynamics as well. So this, of course, also has a lot of limitations that we want to call for research. For example, here we're assuming that it's a static scene to begin with, and really the model really captures is more like a correlation rather than causation. Because what's interesting, what we found when examining the cases, is that you will see that the model predict some things that's also moving in the background. For example, a person walking by from the data when the model when the action is doing something, and that's kind of random and it's not really caused by the robot. So I think that's similar to a lot of the machine learning models today. So this is also something I think that's really important to study. How do we really like train the model for these causal effects more? And it doesn't capture the photorealistic photometric dynamics because it only predicts the movement of the points. So this may be important, for example, in cases where you want to use the model for photometric tasks like turning on or off a lamp or turning on or off a computer or something like that, because you really need the photometric information there to see whether the prediction is correct. And we're also making some assumptions on actuation and tracking. Basically, the assumption is that for the input, we always assume that the actions can be realized. So, for example, you can move the robot to penetrate a wall, a wall, and then like or penetrate the table, something like that. Uh, it's not really possible realistically because due to, for example, the different um, like yeah, just different setup and maybe under different payload, etc. So it's the robot may not, the controller may not really accurately track the actions that we give it to the model, but the model is still forced to predict situation, the scenarios under that situation. So this is also another limitation. So we have this like full page description in the paper. So um, feel free to take a look. And this is something we really want to be transparent and call for research. Yeah. So some closing thoughts. So I think this work it's by itself is a world model. I mean, world model itself doesn't deal with decision making. So, and what it really captures, if we think about it, is physics intuition. So this is really important for kind of the task time inferences that I was talking about to extract novel solutions because it links the actions and state changes. But to really do this kind of system two reasoning, we need to couple that with a goal specification in mind. So what do we want to cause the change to the world? So I think the VLMs that really understand space can do this. We're not sure that the VLM today are fully capable are at that level of performance yet, but we had some early work on how that could be useful to specify this kind of objective. And when we can combine them, then this forms a full pipeline for producing novel behaviors at test time. But all of this is just system two thinking, right? Like, I mean, system two is not enough by itself because we also need system one. And that I think really comes from modeling the motor intuition. So I think this is really going like I think a lot of work in policy learning is mostly capturing this. It's capturing the motor intuition. But I think what will be perhaps more reasonable is for models like those to capture the motor intuition without specific goals in mind. Otherwise, we're producing the behaviors particular for those goals. So if we don't have the goals, then it's a more meaningful way to integrate all of them with physics intuition and goal reasoning. And the hope is that all of them can meet each other in this 3D spatial physical world that we live in by both like grounding the VLM into 3D space and reasoning about the counterfactuals in 3D space and capturing the motor intuitions also in 3D space for the particular geometry of the robot that we care about. Yeah, so with that, that's the end of the talk, and happy to yeah do any discussion or questions.
Hi, Wenlong. Very nice
Yeah.
talk. Yeah, I'm very curious that the work is very good, and I saw that you queued a data set, and will you plan to open source that data set for future research?
Yeah. I mean, the data sets and code and pre-trained checkpoint are all ready. We're we're getting email almost every day to ask for it, but this is a collaboration with NVIDIA,
I
and
see.
it's still under their legal team's review. We
I
really
got
wanted
it.
to get it out as soon as possible. Yes.
Cool. Sounds good.
Yeah.
Thanks.
Hey, Wenlong,
Hello.
can you hear me?
Yeah,
Okay,
yeah,
sweet. Yeah, this is super cool work. Really like it. You had one slide that was talking about the properties of the world modeling. So it's like understanding articulation, gravity, etc. Can you go to that? Yeah,
Is it this one? Okay.
yeah. So I'm just thinking, like, and I'm sure people ask you about this, like. If you think about these, pixel-based world models, they're also able to, for example, do novel view synthesis. Like the novel view synthesis, 3D reconstruction in some sense can be covered by these video world models. Um, but that's just one example, right? But do you think that those models also capture these properties
Yeah, of
similarly?
course.
Hmm.
Yes, yes. Yeah, I think this is a great question. So, yes, I think 2D models also capture the same properties.
Yeah.
Um, and I think why 3D is more valuable in this case, I think it's mostly on the actions.
Hmm.
So this is like a discussion I've been having with a lot of video generation, like folks doing video generation and also doing this generative modeling too. So in generative modeling, I think I also totally agree that actually I think 2D data sources are much more scalable.
Hmm.
But people from that domain also cares a lot about conditioning. I think this conditioning is something we also care so much about in robotics because we really need to control the model not with text but with concrete robot actions.
Hmm.
And one philosophy here that I've been having, and like a one, I guess, like a even strongly held opinion, but of
Hmm.
course, there's a personal opinion, is that I think actions, if we think about our own embodiment, I think actions are fundamentally 3D rather than 2D. For example, if we think about how we can reach our hand into the back pocket of the pants, like we cannot even see that. And we can really move, like close our eyes and move our kind of arms and hand in 3D space. We can easily sense that. And that is fundamentally 3D to me. So I think it's totally plausible that like the input, the seeing like observation is via 2D and generation output is 2D. So that I think the output really depends on the use cases. But the actions, I do think that has to be 3D. And we're just go kind of really to all the way try to unify them in this work. But I can see it's possible that like people build similar things with 2D architectures and 2D input and output.
Right. Yeah. Okay. Yeah. No, this makes sense. The motivation, the philosophy. Cool. Yeah. Thank you.
Yeah, thank you.
Yeah, I will know. Just uh keep I always keep discussing about this question about comparing 3D world model and 2D world model. It's just a kind of technical and technically stupid question. So if given two similar amounts of data of 2D and 3D data, uh, is it uh, is it more expensive or less expensive to train the word model?
Yeah, that's a good question, and I certainly don't have answers for. Um, right. I will say that largely, like when you talk about whether that's expensive, I would
Mm,
imagine you're talking about because you said the same amount of data. So I would imagine you were talking about like the compute efficiency or something like
mm,
that, right? Is that the
correct.
question?
Yes.
Yeah, I think that really largely depends on uh the training framework and the architecture. And by that, I do think 2D is so much more mature than 3D because people do use 2D models so much more than 3D models, and there's the whole infra built around that.
Mm,
And I think that's indeed a huge advantage for 2D to win on the efficiency side.
okay.
Yeah. But that's more on the like the training infra and stuff because
Yeah.
it's just more popular now. Yeah.
So I think the learning efficiency of 3D word model would be much better than 2D because yeah, the information density is higher, right? With 3D representation. Uh,
Yeah, yeah. Okay, so if you're talking about the learning efficiency, I think that's also hard to quantify, but I do share the similar philosophy with you, basically, because the physics happens in 3D, right? So
mhm.
this is much more like a physics simulator
Yeah, yeah,
rather than a renderer, because
yeah.
we're effectively modeling kind of the mesh collision, etc., just without the mesh.
Mhm.
Uh, so I do share that philosophy, but unfortunately, I don't think there's a really good way to quantify that because the output is also different. Here is like the trajectories, uh, like like 3D trajectories, and over there it's more like photometric rendering loss. So it's hard to have a exact one-to-one apple-to-apple comparisons.
Okay. Thank you.
Yeah.
Okay, thank you, Wenlong. Again, we are a little bit run out of time, and
Okay.
thank you again, and looking forward to chat with you in the one-on-one sessions.